Hello and namaste everyone. Welcome to lecture 15 of this NPTEL course on stochastic approximation. Let's do a quick recap of what we did in the previous few lectures. Okay, so in the last but one lecture we sort of discussed conditions for convergence of a super martingale, and of course that implies convergence of a martingale as well, and we said that a super martingale sequence converges if it is bounded in L1, right. Now this condition is often challenging to verify, right. So we then started discussing easier ways to establish Xn's convergence. So one of the ways that we discussed was to show that Xn is bounded in L2 instead of L1, right. So we tried showing it is bounded in L2, and then we said that showing that a sequence in L2 is bounded in L2 is equivalent to showing that the sum of the expected value of the square of the difference between successive terms, okay, that infinite sum, if it is less than infinity, then that is a good condition or sufficient condition to establish Xn's convergence. In fact, we will be using this in the discussion later on, right. And we said that this condition by itself is not going to be enough, or will put restrictive assumptions during our convergence analysis of stochastic approximation, and hence we sort of asked, can we establish a weaker notion or weaker sufficient condition under which we can establish Xn's convergence, right. And towards that we defined this angle bracket process, right. So it is referred to as the angle bracket process because of this notation over here, and formally given a process Xn, the angle bracket process is defined in the following way, that it it's a sum from k equals 1 to n, and you take the conditional expectation of the square of these successive differences, right. And you can see that since k can at most go to n, you will have the last term will be conditioned on fn minus 1, right, which makes an a pre-visible process. Is that okay? So these are things that we discussed in the previous class, and then we stated one result, and which we will be proving today, right. So the results went something like this. It said that suppose you have a martingale, so notice that this result is tailor made for martingales. Suppose you have a martingale in L2, so notice that I am not saying it is bounded in L2, but only saying that it is in L2, which means that we only have that expected value of Xn square is less than infinity for all n. Okay, so this is what is the condition. I have not put a soup over here. If I had put a soup over here, that would have been bounded in L2, so that is not what we are presuming here, right. And for some simplicity, we will presume that the given sequence is null at 0, but this is not a very restrictive assumption. We can take the given sequence which is not null at 0 and subtract x0 from it to make it null at 0, so it is not a big deal, but for simplicity we will presume that Xn is null at 0, which means that x0 is 0, and let an be the angle bracket process. Okay, so what this result says is that your limit Xn exists almost surely on the event a infinity less than infinity, right. So an is this sequence, right, and since Xn is a martingale, one can show that an is an increasing sequence, and because an is an increasing sequence, a infinity exists, right, which can be defined in the following way. A infinity is a random variable, so this will be an event, and the result says that on this event almost surely the limit exists. Is that okay? So you can already see that the sufficient condition over here is very weak, right. It does not talk about boundedness in L2 and so on and so forth. Instead it only says that you define this angle bracket process, and whenever the event holds along all those sample paths, your limit Xn will exist, right. So it is possible that this event has very small probability, right, in which case this will exist. All we are saying is that along the set of sample points in this set, except for a subset of measure 0, your limit Xn will exist. So this result does not say how large this probability is, so that will need to be established externally, right. And then we said let's try to prove this theorem, and towards that we established or started discussing few concepts which I will quickly recall, right. So one of the concepts that we discussed was that of Doobe's decomposition. Okay, so the Doobe's decomposition broadly says that let xn be a process in L1, right, the and which is adapted to some filtration Fn, then the following statements hold. In particular, xn has a Doobe decomposition, that is xn can be expressed in this way, where your mn is a martingale sequence which is null at 0, and an is a pre-visible process which is also null at 0. Is this okay? So the thing to note here is that for this Doobe decomposition to exist, xn did not have any special property. It is just a process that is in L1 and adapted to this filtration Fn, and as soon as you have such a process, we will have this very nice decomposition, right, and an is some pre-visible process. So here please do not misinterpret this an as the angle bracket process. Here an is basically your summation k equals 1 to n expected value of x k minus xk minus 1 given fk minus 1. Okay, so this is how your an process was defined. At least an will equal this almost surely, right. And then we had this additional statement which said that this pre-visible process, right, is a sorry, I should make a correction here. This should not be an, rather it should be xn. Okay, so the statement said that xn is a sub-martingale if and only if the pre-visible process is an increasing process, that is an is less than equal to an plus 1 almost surely, right. So this is if and only if xn is a sub-martingale, then this will hold, and the converse statement that if your pre-visible process turns out to be increasing, then your xn will also be a sub-martingale, right. So now this is a recap of what we did in the previous class. We will now formally look at the proof of this result that we said before, which is this result. Okay, and this result is a bit challenging, and we will need to introduce several interesting concepts, right. So the first of these interesting concepts is the following, right. So when we have been given a martingale sequence xn, what can we say about the xn square process? Okay, so this is the question that we need to answer, and the answer is given in this result. Again, I would like to emphasize that this number over here is taken from this probability with Martingale's textbook by David Williams. So if you need more details, you can look it up, right. So the result goes something as follows. So let xn be a martingale in L2, right, then xn square is actually a sub-martingale, right. So xn is a martingale, and if you look at the square of this individual random variables and consider the resulting process, that resulting process will be a sub-martingale. So let us quickly prove that. Okay, so from Jensen's inequality in the context of your conditional expectations, we know that expected value of f of x given f, right. So if your f is convex, so if you look at the conditional expectation of this, then this will be greater than equal to f of expected value of x given f. Okay, so this was the Jensen's inequality for the case of conditional expectations, right. So invoking that over here, we get something like this. So the question is, what is the f that we are using over here? Well, it is straightforward to guess. The f that we are looking at is f of little x equals x square. Now it is obvious to check that this function is convex in nature, and hence this inequality over here applies. So you can see that you have xn square here. Okay, so that is f of xn plus 1. So if you take the conditional expectation of that function goes out, and you are left with the conditional expectation of xn plus 1 given fn. Now since your given xn sequence is a martingale, this expression will turn out to be simply xn, right, and then you have a square over here. So together we end up with xn square, Is that okay? So what we have managed to show is that the conditional expectation of xn plus 1 square given fn, right, is greater than equal to xn square, which immediately tells us that this xn square is a sub-martingale. Is that okay? So now we need one more important concept in order to have the requisite material to prove this theorem 12.13 that I stated before, and that concept is that of stopping time, right. So in the context of martingales, this stopping time actually plays a very important and useful role, and it is understanding this concept very well will help you come up with very innovative ideas while proving convergence of martingales or super martingales. Is that okay? Alright. So the question is, what is a stopping time, right? So to define a stopping time, we begin with a filtered space. So what is a filtered space? You have the sample space, you have some sigma algebra, and then you have a sequence of sigma algebras, okay, which satisfy the property that fn is a subset of fn plus 1, right. So this property needs to be satisfied, right, and each of them of course is a subset of f, and then we have some probability measure p, right, and on this we have a random variable which is defined, right. So random variable is a function which goes from this sample space omega, and this time we allow t to take values either between either any integer which is larger than equal to 0, and we will also allow t to take the value plus infinity. So either it takes a non-negative integer or the value plus infinity, right. So you have such a function, and we will refer to this function as a stopping time if it satisfies this condition. So let us understand this condition. So t less than equal to n, okay, is an event. So which basically means you identify all those omega in capital Omega such that t of omega is less than n, right. So you consider this collection of omega, so this will form a set, and this set should belong to fn for all n greater than equal to 0. So notice that the dependence of n comes in over here, right, and we will now show that equivalently this condition is is similar to saying that t equals n, this event belongs to fn for all n greater than 0, okay. So I want to give an intuitive explanation of what this means, but before we do that, let us quickly see why this condition and this condition should be the same, right. So first let us presume that this is true, right, and using this we will show that this statement holds, right, and I hope you agree that t equals n is equal to the event t less than n intersection t is strictly bigger than n minus 1, right. So I am just carefully writing the event t equals n, right, in this following way, that it should be less than equal to n and it should be strictly bigger than n minus 1, and only then t will equal n, right. Now this event over here can be written as a complement of t less than equal to n minus 1. So now one can ask, okay, what is the utility of expressing t equals n in this fashion, right. So now we have been told that this belongs to fn, and similarly this belongs to fn minus 1, and since this is a subset of fn, okay, this both these events belong to fn, and since fn is a sigma field, if two events belong to fn, then their union will their intersection, finite intersection, will also belong to fn, and from this one can conclude that t equals n also belongs to fn, right, and one can similarly show the converse, right, that by making use of the fact that the event t less than equal to n can be expressed as this finite union of k equals 0 to n t equals k. Is that okay? So it is very easy to see why this equality holds, right, and we have been now told, like we are in the converse statement, so we have been now told that each of this belongs to Fk, which is a subset of Fn, and hence every event here belongs to Fn, and this is a finite union of events in Fn, and hence this should also belong to Fn. So what we have managed to show is that these two definitions of stopping times are equivalent. So again let me repeat. So a random variable t which takes values in the set of non-negative integers or plus infinity, right, is said to be a stopping time if either t less than equal to n belongs to Fn for all n greater than 0, or equivalently t equals n belongs to Fn for all n greater than equal to 0. Okay, so we have now verified the equivalence between these two conditions. So now what we will do is we will look at an intuitive description of a stopping time. Is that okay? So recall that typically we define Fn to be the sigma field that is generated by x0 to xn. This could also be some given filtration, which need not be this, but it could be either different or more elaborate than this, but this is an the typical sigma field that we consider, right. So in this context, right, when we say t has the property that t equals n belongs to Fn for all n, it is equivalent to saying that this event over here t equals n is in some sense expressible in terms of events that only involve x0 to xn, right. In other words, t equals n belongs to Fn is equivalent to saying that the event t equals n, right, is expressible in terms of events involving only x0 to xn. Is that okay? And in other words, we can also interpret the notion of a stopping time in the following way, that by just looking at the information that is available at time n, which is like the values of x0 to xn, one can conclude whether the event t equals n has occurred or not. Is that okay? So this is very important. I am not saying that one should be able to say t equals n has occurred or it has not occurred. One of the two, if you are able to say it unambiguously, then we will say that your t is a stopping time. So let us look at some examples, and that will help clarify the details, right. So let us say xn is some stochastic process adapted to Fn. I mean, this Fn need not be the sigma field that I introduced previously, this could be some arbitrary Fn, right, and let us say A is some subset of R, like for example this could be the set of non-negative real numbers and so on and so forth, and let T be defined to be the inf over n of the event xn belongs to A, right. So what this is saying is you are looking for the first time at which the process xn belongs to A, that is it is the first time xn takes a value that lies in A, right, and this is also referred to as the time to hit A, right. Okay, so that is what I have said over here. T is the first time for which xn belongs to A. Now it is possible that along a sample path xn never takes a value that belongs to A, right. In that case this set will be empty, and in that scenario we will use this convention that inf of an empty set is plus infinity to conclude that on that sample point t equals plus infinity. Okay, so I have said that t equals the value of plus infinity if xn never hits A. So again I would like to elaborate what this means a bit here, right. So we have to interpret this definition on a sample point by sample point basis, which means that t of omega equals inf n greater than equal to 0 xn of omega belongs to A. Is that okay? Alright. Okay, and now the question is this time that we have defined, the first time to hit A, is it a stopping time or not? Okay, so you can see that for this notion of t, right, the event t less than equal to n is equivalent to the union that xk belongs to A. So let us just understand, t less than equals to n means that at some point less than equal to n your process was taking a value in A, which is exactly what is written over here, right. And because you can express t less than equal to n in this fashion, and we know that your xn process is adapted, and in particular xk belongs to A must belong to fk, and fk is a subset of fn, hence every event here belongs to fn, and hence their union must also belong to fn, which can help us conclude that this belongs to fn for all n, and we can finally conclude that t is a stopping time. Is that okay? So I have now given you a very simple example of a stopping time. Let us now look at an example which is example of something that is not a stopping time. Okay, so here is that example, right. So let L be the random variable which is defined in the following way. It is the supremum, and let us say the supremum of n within the indices 0 to 10 such that xn belongs to A, right. So this says that what is the last time that xn was in A, right. So that is what describes L, and again it is possible that so this set could be empty, in that xn was never in A, in which case this will be empty, and we will use the convention that supremum of an empty set is 0. Okay. So this is the convention that we will use. So let us try to understand whether this L is a stopping time or not, and one can check very easily that the event t equals 1, okay, equals the fact that x1 belongs to A, right. So this is the supremum, sorry, I think I made a mistake over here, this should be L. Okay. So the event L equals 1 corresponds to x1 belonging to A, and this should be the last time you should be in A, which implies that for every k which is from 2 to 10, your xk should not belong to A, right. So we want this also to happen and this also to happen, right, and for a general choice of A, this belongs to f1, but these events need not belong to f1, and hence in general this intersection need not belong to f1 for a generic choice of A, right. And since this does not belong to f1, okay, one can conclude that L is not a stopping time. Okay. So I hope after looking at these two examples you have some sense of what is a stopping time and what is not a stopping time. The loose summary is that t is a stopping time if the event t equals n, you can say whether it has occurred or not based only on the information that is available from time 0 to n. Alright, very good. Okay. So as I told you, this theorem 12.13 is a bit challenging and we require a lot of concepts, right. So we have now understood this dupe decomposition, and then we have understood this property of xn square when xn is a martingale, right, and now we also introduce this concept of a stopping time, and now we will see the power of stopping time via this result. Okay. So again this number over here is taken from this probability with Martingale's textbook by David Williams, right. So what does this result say? It says that suppose xn is a super martingale, right. Suppose xn is a super martingale and t is some stopping time, right. Then the process xnt, which is referred to as the stop process, right, is also a super martingale. Okay. So the result says that if you start with a super martingale, then the stopped process is also a super martingale. So what do we mean by stop process? I will now try to explain. So xnt is defined to be x of n min t. Okay. So this notation over here is defined here, right. So n is an integer, t is a random variable which on different sample points will take either a finite integer or plus infinity, right. So in either case we can look at the min of these two values, right, and this is what this notation over here means, right. So let us spend a few seconds in understanding why this process is referred to as a stopped process, right. So let us try to understand or try to make sense of this definition for some sample point omega, right. So for little omega, you would have some t of omega, right. So then x of x n min t of omega, right. So this now makes sense, right. Like for example, if your t of omega is 5, right, this will be like x n min 5 of omega, right. So we can understand this value for different values of n now, and one can immediately see that if n is strictly less than equal to t of omega, right, then the min will basically be n, hence this value will equal this value. On the other hand, if n is greater than equal to t of omega, then this value will equal this, right. Now if t omega is 5, right, so for every n which is bigger than equal to 5, your x n t of omega will equal x 5 of omega, right. So if you even if you keep increasing n beyond 5, 6, 7, 8, whatever you want, the value of this will stay at x 5 of omega. So you can see that at for all large enough n, the value of this process, okay, will be xt of omega, and that is why we refer to this process as a stopped process. Is that okay? Alright. So now our goal is to show that if xn is a super martingale, then the stop process xnt is also a super martingale, right, and this is proved in a very clever and easy fashion, and we will go over it now, right. So the idea over here is to define a new process Cn, okay, given by Cn equals indicator n less than equal to t. Is this okay? So again, this is a random variable, since Cn of omega equals indicator n less than equal to t of omega. Alright, so this is what we have, right. Okay, and now what we will do is we will let yn be this process over here, right. So it is like the sum of ck times xkt minus xk minus 1t, right, and I am claiming that this sum is equal to this sum, right. So the difference between this sum and this sum is that here you have t, whereas here you do not have t, which means that this sum over here is expressed in terms of your stop process, whereas this sum over here is expressed in terms of the original process, right. So let us see why this is why this equivalence holds, right. Now notice that whenever ck is 1, right, so from the definition of Cn over here, one can see that whenever ck is 1, we have that k is less than equal to t, right. So whenever ck is 1, k is less than equal to t, hence this difference must equal xk min t and xk minus 1t, and since k is less than equal to t, this expression must equal xk, and this expression again, since k minus 1 is less than k and k is less than t, this must also equal xk minus 1. So in other words, this difference must equal this difference over here. Is that okay? So what we have managed to show is that whenever ck is 1, this expression equals this expression. Now it is also possible that ck is 0, but if ck is 0, it does not matter what I have over here, because this product will be 0. Is that okay? So hence we do not have to worry about what is this value when ck is 0, we only need to worry about what is this value when ck is 1, and we have shown that when ck is 1, these two things are the same, and hence one can conclude that this sum equals this sum over here, right. However, once we have this relation, we can easily conclude something. Okay, first we can see that Cn is a pre-visible process, right, and I will show you how that can be shown. But if Cn is a pre-visible process, then one can use one of the results that we have proved earlier to show that yn using this fact, okay, must be a super martingale. Since xn is a super martingale, yn is also will be a super martingale. Okay, so that fact we can immediately conclude, right. So let us quickly check why Cn is a pre-visible process. Okay, so for this what we will do is we will look at the two events that can be defined in relation to Cn, right. So Cn is a indicator random variable, so either you have Cn equals 1 or Cn equals 0, and they are complements of each other. So let us focus on the event Cn equals 0, right. So what does Cn equals 0 mean? Let us recall the definition of Cn. So Cn equals 0 means that your so here we have n less than equal to t, or t must be greater than equal to n for Cn to be 1. So Cn equals 0 means that t is strictly less than n, right. So t is strictly less than n means that this is the union k equals 0 till n minus 1 t is k. Okay, so this event equals this, and because this is n minus 1 over here, we know that this union must belong to f n minus 1, right. So since your Cn equals 0 belongs to Fn minus 1, and since Fn minus 1 is a sigma algebra, one can immediately conclude that Cn equals 1 must also belong to Fn minus 1, which in turn implies that Cn is measurable with respect to Fn minus 1, and hence Cn is a pre-visible process, right. So and as I said, since Cn is a pre-visible process, by using one of the previous results we had proved, one can conclude that since Xn is a super martingale, we immediately have that Yn is also a super martingale, right. But one can now use an alternative description of Yn, right. So Yn was defined in the following way, right. Now as soon as Ck becomes 0, right, whatever you add over here, you are only adding 0 terms over here, right. So from that observation, one can see that Yn has this equivalent description. Is that okay? So let us just understand this, right. So from some value, okay, let me just see if I can explain it in a better way, right. So your Yn sequence, your Yn sequence was summation k equals 1 till n Ck xk t minus xk minus 1 t. Is that okay? Now where was I? Yeah, so I should say Yn equals summation k equals 1 to n Ck xk t minus xk minus 1 t. Is that okay? Now one can immediately see that for any omega, if n is larger than t of omega, then for all those values of k, right, your Ck will be 0. Hence these terms will be 0, hence it suffices to only look at this sum over here, right. Now for k which is between 1 and n min t, the value of Ck is 1, hence we can replace this Ck with 1 over here, and this expression will become this. But once we write it in this way, we have a telescopic sum, and hence we will only end up with the last term in this sequence, which is xn t, right, and the first term over here, which is for the value of k equals 1, which is x0 t, right, and it is easy to see that x0 t is actually x0, right. So we have xn t minus x0, in other words your xn t is actually equal to yn plus x0. Is that okay? And since we have proven earlier that Yn is a super martingale, it follows that xn t is also a super martingale. And by repeating the proof argument, one can also show the following, that if xn is a martingale, not just a super martingale, if xn is a martingale, then your stop process will also be a martingale, right. So let me summarize quickly what we have shown. We have shown that if you start with a super martingale and you stop it, then that stopped process will also be a super martingale, and similarly if you start with a martingale, then the stop process will also be a martingale. Is that okay? So now I proved theorem 12.13 as promised. Is that okay? So I want to keep this as an exercise so that those who are listening to this video, okay, can try proving this on their own. So I am going to basically build upon all the results that we have seen so far, right, and prove theorem 12.13. Is that okay? So recall what we had to show in theorem 12.13. we had to show that your limit xn exists almost surely on the event a infinity strictly less than infinity. Is that okay? And we have not been told that xn is bounded in L2. So we have been just been given some xn process in L2, not bounded in L2, right, and we need to now show that it converges almost surely on the event a infinity less than infinity, right. So what we will do is we will first work with this square process, that is xn square, right, and we know that since xn is a martingale, this will be a sub martingale, right, and now since xn square is sub martingale and hence some process, right, we can invoke the dupe decomposition to conclude that xn square can be broken down into mn plus an. Is that okay? Where mn is a martingale and an is a pre-visible process. So if this was an arbitrary process, right, then an has some structure, but since you have xn square over here, one can show that an has this precise description, right. I encourage you to figure out why this description holds, right. So the pre-visible process has this precise description, and this process, if you recall, corresponds to the angle bracket process associated with xn. Is that okay? So let me summarize. From the deep decomposition, we know that xn square can be expressed as mn plus an, right, and an has this description which corresponds to the angle bracket process corresponding to xn, right. So in the proof of 12.13, the clever thing that is used is this definition of this stopping time. Okay, this is, you can once you read this proof and understand, you will see that this is a very clever definition of the stopping time. So what we do is, let sk be the first time where an plus 1 is strictly bigger than k. Okay, so notice this plus 1 over here, and that actually plays a very crucial role throughout this proof. So sk is the first time where an plus 1 is strictly bigger than k, right, and one can check that because an is pre-visible, even though you have n plus 1 over here, one can show that your sk is actually a stopping time for any k. Okay, so one can actually show that. Okay, and I encourage you to prove this, I am not proving this, and separately one can show that the stopped process ansk. So what is ansk? So ansk is basically an min sk, right. So this is what ansk is. So one can show that the stop process ansk is also a pre-visible process. So again, I encourage the listener to actually verify this fact on their own, right, and let us now define yn to be xn stopped at sk, right, and since xn is your martingale and sk is a stopping time, then one can immediately conclude that yn is a martingale, right, and moreover, if you look at the the angle bracket process associated with yn, then one can show that the angle bracket process associated with yn is the the process an which is stopped at sk. So let's summarize what we have done, right. So an is the angle bracket process associated with xn, and if we define sk in this way, and you stop xn at sk and define yn, then yn is a martingale, and the angle bracket process of yn is related to the angle bracket process of xn, in that the angle bracket process associated with yn is the angle bracket the stopped angle bracket process associated with xn, right, and that stopping has to be with sk. Is that okay? And again an because it is the angle bracket process, one can see that this has the following description over here, right. So because it has this description, we can take expectation on both sides to conclude that expected value of a min sk is the sum of these expectations, right. So we are invoking the linearity property and the iterated expectation property to make this conclusion, right, and then one can see that because your yi's are martingales, this expectation actually turns out to be the difference between the squares, that is, you can check what happens with the cross term, and because we have the difference of squares, we have a telescopic sum, right, and we can cancel off corresponding terms, and we will end up with expected value of yn square minus expected value of y0 square. And if you recall, in the statement of this result we have assumed that your xn's are start at 0, that is they are null at 0, and hence one can show that from this definition your y0 must also be 0, and hence y0 square must be 0, and hence the expected value of y0 square must be 0. In other words, this expectation must equal this expectation, right. So now from the definition of your sk, right, from the definition of sk, recall that sk was the smallest time such that a n plus 1 is strictly bigger than equal to k, right. And notice that here you have n, right, and we are taking n min sk, right, and sk is defined in terms of a n plus 1, right. So we can show that until you achieve this or you hit this set, right. So a n min sk is until you hit that set, and since you have not hit this set, in other words your a n values are still bigger than equal to k, one can conclude that a n min sk is actually less than equal to k for all n, right. So this is a very important conclusion, you will soon see why, and it is a very interesting conclusion which just follows from this definition of sk and the fact that you have plus 1 over here, right. So once we know that this is less than k for every n, right, one can conclude that your expected value of a n greater than sk will also be less than equal to k, right. And since in the previous slide we show that this expectation equals this expectation, one can conclude that the expected value of yn square is less than equal to k on for all n, right. So the left hand side, right, is varying with n, and on the right hand side you have no n, and hence one can conclude that your yn process is bounded in L2, right. So while the given xn process was not told to us to be bounded in L2, one can show that the stopped process is actually bounded in L2, and now if you remember one of the first results that I discussed in today's class, we can invoke that to conclude that yn converges and converges to a finite number almost surely, right. So what we have managed to show is we wanted to show xn converges. So towards that what we did was we defined a stopped process yn, right, and we are saying that the stopped process converges, right, and we can define yn the stopped process with respect to sk for any k, right. So so we can define that, and what we are saying is whatever sk you pick over here, for every k sk is a stopping time, so whatever sk you pick, your yn will be a stopped process, and the conclusion holds, right. Now okay, let us look at this event a infinity is less than infinity, right. So a infinity less than infinity is, recall, the event of interest for us. In particular we want to show that a infinity less than infinity is the event on which almost surely limit xn exists, right, and one can very easily see that from the definition of sk that is given over here, right, from the definition of sk that is given over here, okay, from the definition of sk that is given over here, one can conclude that if a infinity is less than infinity, right. So let us elaborate a bit. So a infinity is less than infinity means that a infinity of like if omega belongs over here, then that means that a infinity of omega is less than infinity, right. So less than infinity means it is going to take some finite value, right. Let us say a infinity is let us say a infinity of omega is, let us say, 5 as an example, right. So if it is 5, and because your this a n process is defined with respect to your xn square, and since xn square is a submartingale, your a n is monotonically increasing, right, one can conclude that your a n of omega, okay, this is less than 5 for all n, right. So a n of omega is less than 5 for all n, right, and since it is less than equal to 5, right. So if you pick a k which is larger than 5 or bigger than 5, then one can conclude that this event will never happen, right, on this omega, right. So, on this omega your an plus 1 omega will never be bigger than k, where k is chosen to be 5, in which case this will be an empty set, right, and since this is an empty set and by convention we have that corresponding sk will be infinity. So, from that observation one can see that a infinity is less than infinity will only happen if sk equals infinity for some k, right. A infinity is less than equal to infinity if sk equals plus infinity for some k, right. So, if this happens, we have that if you have an omega in this event, right, then omega must belong to sk equals infinity for some k, right. Now, if you take such an omega, right, which belongs to this, then for this omega your limit xn of omega actually equals limit xn min sk of omega, right. So, why does that happen? Because for this omega your sk of omega is actually infinity. So, n min infinity is n, hence this xn and this xn min infinity is going to be xn only, and hence their limits have to match. However, we know that the stopped process limit always exists or almost surely exists, right, and from that observation one can conclude that on such an omega your limit xn exists, okay. And if you think a bit about this, what this implies is that almost surely on this event your limit xn actually exists by using this fact over here, and we can now conclude the desired result. So, this brings me to the end of the class. Let us just quickly summarize what we have done in this class and in particular throughout this week. In this class we have established a weak condition for convergence of martingales. In particular we defined this angle bracket process, and we said that whenever the angle bracket process is less than infinity, almost surely on that event your limit xn exists, right, and we for that we made use of this stopping time concept and proved that result, okay. So, this summarizes what we did in this class. Now let me summarize what we have done throughout this week, right. So, throughout this week we have studied about martingales, convergence of martingales. In particular we made use of this Dup's upcrossing lemma and so on and so forth, and finally we have established one condition based on this angle bracket process that corresponds to the condition under which we can establish convergence of a martingale, okay. So, this property or this last theorem 12.13 we will be using during our convergence analysis of stochastic approximation, right. So, in the next week we will actually be discussing another topic or another fundamental topic, which is that of ordinary differential equations. So, martingales is one topic that we have discussed so far, then we want to discuss ordinary differential equations, which will be a separate topic, and stochastic approximation in some sense is a combination of understanding of ordinary differential equations and martingale theory put together. So, with that let me stop. Thank you, hope to see you next week.